Welcome to CSAI Think Tinker Learn. This is part of my System Design Essential series. The goal here is to give you a solid mental model of system design topics. We're breaking down scaling reads, replicas, and query routing today. This being a concept first introduction to help you build your system design foundation quickly. If you want a deep dive on any of the trade offs or a specific case study, let me know in the comments. No fluff, let's get into the technicals. To understand why we scale reads, we have to look at why scaling up or vertical scaling eventually fails. Most web scale traffic profiles are heavily skewed, with 80 to 90% of traffic being reads. On a single primary node, these reads compete with writes for resources. The critical failure here is lock contention. When your reads saturate the CPU and memory, writes begin to fail because you can't acquire the necessary locks. The system hits the gridlock that no amount of expensive hardware can fix. The solution is the primary replica pair. Think of the primary as the back office where the master collection is managed. This is where all the ACID compliant writes happen. The replicas are like reading rooms. We use asynchronous replication to stream the write ahead log from the back office to the reading rooms. This linearly adds capacity. N replicas roughly equals n times your previous read throughput, allowing you to serve millions of users without melting your primary node. However, this architecture introduces a core failure: replication lag. In an asynchronous system, there is a delay between a write hitting the primary and appearing on the replica. This leads to the missing data bug. Imagine a user uploads a photo to the primary, refreshes the page, and the router hits a lagging replica. The user gets a 404 error, even though the data exists on the primary. Stale leads like this destroy to users' trust, which is why we can't just randomly assign traffic. To manage this complexity, we use a proxy router. Implementation like pgpool2 or AWS RDS proxy sit between the application and the database. This centralized routing is clean, but as a senior engineer, you must account for the Stabilo Red, the extra network hop. This adds latency. You also have to be careful about connection storms if your connection pooling isn't configured correctly at the proxy level. Let's look at the actual routing logic under the hood. Every millisecond, the router follows the strict decision tree. Step 1. Is it a write? If yes, it goes straight to the primary. Step 2. If it's a read, check the lag. Using functions like pg last exact replay timestamp, we check if the replica is too stale. If the lag exceeds our SLA, we failsafe back to the primary. If the lag is acceptable, we move to step 3 and load balance the query across healthy replicas. Where should this logic live? Use the routing topology matrix to decide. App level routing is fine for small SaaS apps, but has a high maintenance overhead. DNS based routing is cheap, but very slow to update due to TTL. Proxy based routing is the general purpose sweet spot for most architecture because it provides a good balance of complexity and consistency control without forcing you to rewrite your application code. As an architect, you need to be consistency aware. Think of it as a set of switches. Strong consistency forces everything to the primary, essential for financial transactions. Eventual consistency allows read from any replica, perfect for social media feeds. The middle way is bounded staleness. We only route to the replica if the estimated lag is below a certain threshold like 35 milliseconds. This is the best choice for high performance dashboards. We solve the missing data problem for the active user via session pinning. This ensures read your write per guarantee. When a user performs a write at t equals 0, we pin their session to the primary database for a very short window, say 200 milliseconds. This bypasses the replication lag entirely for that specific user. Once the lag window passes at t equals 200 milliseconds, the pin lifts and the user reads resume via the replicas. Warning: never pin globally or your primary will collapse. What happens when you need dozens of replicas? A single primary's network card will physically saturate, trying to broadcast the WAL stream to everyone. The solution is cascading replicas. Tier 1 replicas pull from the primary, the Tier 2 replicas pull from Tier 1. While this saves the primary, it creates a complex failure domain. If an intermediate Tier 1 node fails, it causes cascading data starvation for all the Tier 2 nodes beneath it. The stack is constantly evolving. In the 2000s, we were wrecking bare metal servers for master slave setup. By 2013, we had dumb proxies handling basic routing. 2018 brought us cloud native auto scaling pools like Amazon Aurora. Today, we are moving into the ML driven adaptive routing in systems like Google Spanner. The cloud provides ha- the cloud handle the hardware now, but they don't know the business logic. You still need to know exactly how the router thinks. To wrap up, here is a senior engineer pre-flight checklist. Measure your read-write ratio. If it's not mostly reads, replicas won't help. Quantify your staleness (SLA) for different parts of the app. Implement lag alerting, and always test failure scenarios by killing a replica to see how the router adapts. The final rule: we never sacrifice write consistency for read speed unless the business explicitly sign off on it. Now, a question for you. How do you handle read after write consistency in your current project? Do you use session pinning, or have you found another way to hide replication lag from your users? Let me know in the comments. If this blueprint helped you, please like, share, and subscribe to CSEI Think Tinker Learn. See you in the next one.